All right, let's see if we can talk about some induced charge, some electrostatics, maybe some circuits, pretty much everything you need to know for your homework. Well, this thing called induced charge is where you can have a neutral object, let's say this is like the wall, and the wall has protons, it has electrons, it has neutrons too, but let's not worry about those. Um, but pretty much a wall or any object that's around you is probably neutrally charged. And if you bring a charged object close to it, what's going to happen is that it's either going to push away or pull towards the surface here the electrons that are able to move. And so if we have this balloon, and let's make this balloon, let's say, really positively charged, if we took this balloon and we moved it towards the wall, what'll start to happen is, if you've done this before, then this balloon is going to kind of be attracted to the wall, or it's going to seem like it gets stuck to the wall, and that's a horrible balloon. But that's what I get for not really looking. But this balloon, you bring it to the wall, and it seems like it's stuck to the wall, like it has a force of attraction that would be towards the wall. Well, if there's a force of attraction towards the wall, that means the wall should have a force of attraction towards it. And so you wonder, like, how can this happen if you have two things where one you know is charged, but the other one it's supposed to be neutral? Well, we call this induced charge, where if we bring this positively charged thing over to the wall, it's going to attract a lot of the electrons that are able to move within the wall itself. Okay, so conductors have electrons that are really, really able to move. They're really easy to move, whereas insulators, it's a little bit harder to get those electrons to move. So if we had a balloon that was, let's see if we can do a better balloon here. Slightly, happy birthday. But if we had a balloon that was negatively charged and we brought it close to this wall, you'd still feel a force of attraction of the balloon towards the wall, and the wall would still feel a force of attraction towards the balloon because of Newton's third law. But instead of the electrons getting attracted towards the balloon, it would actually repel electrons away, leaving an area of more positive space. And so we have this attraction again between charges that are oppositely charged. Okay, so induced charge is where you can actually bring one charged object close to another one and induce a charge on that neutrally charged object because you're sending the electrons away or you're bringing the electrons closer towards it. If you actually touched the balloon to the wall, then there would be a transfer of charge. If you touch this positive balloon to the wall, then these negative charges that have been attracted to it will jump over, whereas if you have a negatively charged balloon and you touch it to the wall, then these negative charges, these electrons, will jump over to the wall itself. And so to get things to actually jump over and move, you've seen in class whenever I've got shocked by the Van de Graaff generator, or I've shocked you guys, you've actually seen those electrons moving through the air because there's enough force there, there's a high enough electric field to actually move those things. So the equation that we're talking about as far as force goes between charges is this one, KQ1 Q2 over R squared. And what this represents is the force of attraction between two charges due to being in a field, particularly in an electric field. So kind of like gravitational field, it's got the exact same setup. It's relying upon the distance squared on the bottom. From the class the other day, K is 9 times 10 to the 9th Newton meters squared over Coulomb squared. That's the C there. That's the unit of charge, Coulomb. This is Coulomb's equation, or Coulomb's law, between electric charges. Q is the electric charge itself. It could be positive or negative, but what we know is that positives and positives repel, negatives and negatives also repel, positives and negatives attract. So I'm not too worried about the sign. And then we're looking at R, which is the distance between the two, or sometimes you guys always call it the radius. It's just the distance between those two things. And this will be measured in meters. And charge will be measured in coulombs, just like Coulomb's law. All right, so we've got the force of attraction between two things, or the force of repulsion between two of these charged things. And the whole reason why this happens is because you place one charge in somebody else's field. So if we come down here, and let's say we have one of those positive charges and one of those negative charges, essentially what's happening around each and every one of these charges is they're creating what's called an electric field. And this electric field goes out in all directions with the positive charge. And I'm not going to draw too many of these because I'm doing a video, but you get the idea. So around the positive charge, they're all going out in all directions, whereas with the negative charge, it's going in all directions. Okay? And these are vectors. So if you think about a vector, whenever you combine vectors, let's say right here in this point in space, we would have a vector from the positive charge going straight away from it, whereas with the negative charge we'd have a vector going straight towards it. And these two vectors combined would give me a vector overall that's probably going to the right. Okay. Same thing if we go down here, I can see that from this positive charge I'd have a vector going straight away. If I have a negative charge, then I have a vector going straight towards it. And if we combine these two, then I have a vector that's most likely going to the right. Okay, and so what happens is if you have a negative charge and a positive charge in the vicinity of each other, then you get fields that tend to look like this. And my green pen sucks, so let me use this. Okay, so these field vectors are going to kind of curve over and go from positive to the negative. And the more field lines you have, that kind of means that there's going to be a stronger field there. So if you missed this from class the other day, this is kind of what we talked about. So if you have positive and negative, field lines will go from positive to negative, and if one's a lot more charged, then we're going to draw more field lines there. Okay, and field lines are vectors, so if you want to find the strength of a field, well, you just kind of look at this equation, and it changes very, very slightly. For the electric field, we're looking at an equation that looks like this, KQ over R squared. And all that's saying to us is that if we want to find the strength of this field at any location, then we just need to know the distance away from a charge creating that field and the charge itself. Okay, so if I wanted to know the field at this location right there, then I know that from the positive charge, it points to the right. From the negative charge, it also points to the right. And so in the end, what I get are the two fields, one from the positive and the other one from the negative, that we would have to add together as vectors to equal the total E field at that point, or the net field. Alright, and so we're looking at KQ over R squared plus KQ over R squared as far as these two. So Q here would be this Q would be this negative Q, and the distance would be whatever this distance is here. Okay, or this one over here. So we add vectors, we add field as vectors. Another thing on your homework, kind of moving through, is there is something called resistivity, and we need to talk about current as far as all that goes. So this is like a compilation video of everything you need to know for your homework if you wanted a video lecture. This is just in the case that I'm not in class. So if you imagine this is a wire, alright, a wire is made up of molecules, it's made up of atoms, it's got stuff inside of it essentially. So if you have a wire that's made up of all this stuff, imagine a pipe, like a pipe with a bunch of crap inside of it. But what you're going to try to do is you need to move some electrons through it. So here's electrons, they're trying to move through it. The issue with the electrons, though, is that they can't go straight through unless we have something called a superconductor. A superconductor has a structure that's basically like an open hallway. But in your passing periods, if you think about the hallway, just imagine the hallway real quick. In passing periods, there are people. And there are slow people, and there are fast people, and there are those people that stand in the middle of the hallway. Those are the people that I yell at. But if you have people in the hallway, then you have people that are in your way. And if you are the electron trying to get through, then maybe it's not the best option to go straight through. Maybe you need to take some turns. Maybe you even need to go backwards in order to get through this hallway. And this is actually what happens for real. So these electrons in these DC circuits, or these direct current circuits, maybe they can get through straight away. Maybe they can't because something's in the way. Maybe they have to go backwards because, well, they just do that. But overall, their motion is going to be in a certain direction. And that's what we call current. So current is this flow of charge, or you can think about it like water. So this current is kind of this flow of charge. And really, by convention, this is what is kind of weird, is that current is the flow of its positive charge. Alright, and what we know now is that it's actually negative charge. This is just one of those things where it was quoted one way. Benjamin Franklin said that it was the positive charges that were moving, and we later found out that whenever we assign charges a symbol or a sign, it was the negative charges that were moving. So they just kept it like that. So flow of positive charge, it's actually the electrons that are moving. I know, it's weird. But we have it. It's called current. Current is the charge, the change in charge that goes across the position per time. So we have coulombs, as far as units go, coulombs per second. So if you have charge flowing by, it's coulombs per second, and it's also known as the amp, or the ampere. All right, that's going to be an A. So with charge, if you have current, then you have charges flowing by per second, and if you can count those, we're counting individual electrons, or I guess you want to call them positrons or protons, the positive charges, same thing, flowing by a period per time. All right, so that's going to be what we have with a wire. Now they're going to have an easier time of flowing through if there's less resistance or crap in the way, and the way that we figure that out is going to be this thing called resistivity. These are my little notes of what I need to talk about. So for a wire, resistance, in other words, the stuff in the way, imagine the people in the hallway, is equal to this thing called resistivity. And if you think about a hallway, if you're trying to go from period to period, the longer the hallway is, the more stuff is probably in your way. But the bigger the hallway is, the easier it is to move through it because you have more room to move. And that's what this equation kind of represents. This rho is the resistivity of the material. Okay, and so different materials like copper, like gold, silver, those are pretty good for resistance. So we're looking for a low resistivity there. Whereas if you have wood, or if you have, I don't know, rubber, then it would have a high resistance per length of the stuff. The longer it is, the worse off you are. Okay, I'll do it that way. So that'll be length, and then this will be area of your thing. So your area could be like the cross-sectional area of a box, or a cross-sectional area of a cylinder, for instance, or this would be a circle for the area. So for the resistance of something, that's going to be the resistivity times L divided by A. The longer the thing is, the more resistance it is. The bigger the thing is, the less resistance it is. And resistance is measured in the ohm, or the omega. All right, so resistance is going to be ohms. Now, the more resistance it has, the more energy can be dropped off by the current. The current, imagine it like water, it's got a lot of energy with it, depending upon what's called the voltage. And if it moves through resistance, the thing's going to get hot. All right, you have these electrons bumping through, they're going to release some energy there. And so we have this other thing called Ohm's law. I'll just star that as far as the video is concerned. And Ohm's law is going to be V equals IR. This is going to be one of the things we're using the most. V is representative of voltage, and some people call that like the push behind the current. It's kind of what gives the current energy. It is electrical energy. I is current itself, and R is this thing that we call resistance. So Ohm's law deals with the things that are in a circuit or in a wire, the current that's pushing through, and the voltage that's actually pushing it. So if we wanted to talk about a circuit diagram, we can draw ourselves a battery. This is a battery. And these are the wires that come out of the battery. This is going to be the plus side and the negative side. And we'll do this in class too, I'll promise you that. So don't worry about, oh my gosh, he's only doing it in video form. I can't do this because I need to be in class where I also don't really pay attention. Actually, the most learning that you do is whenever you do it yourself. At least that's what I've found in my years of teaching. So I can teach you all day long, but until you do it yourself, you're not going to get too much out of it. So, battery right there. These are called resistors. Imagine they look like little mountains. So these are resistors, and then this thing here is going to be the wire, and then we're going to say it's the flow of positive charge, so positive goes to negative. So my current would be flowing this way. Okay, so the battery, let's say it's like a 9-volt battery. The resistors, we'll make them just 100 ohms here, and maybe 150 ohms here. And this is going to be a little walkthrough for the end of your homework. But if we have this current, if you look at the current needs to flow through both of these resistors. So how much resistance does the current need to flow through? Well, in this is called a series circuit. All right, and we'll talk about this again. But the series circuit, it has to flow through this much and this much. So a total resistance for this whole circuit is going to be 250 ohms. All right. The voltage provided in this circuit is going to be 9 volts, and the current is going to be unknown. Now, this is a very, very simple circuit, so they get a lot more complex. You also have like AC circuits, alternating current, but this is just a DC circuit where the current only goes one way and doesn't flip. And what we can look at is Ohm's law, V equals I R, and really it's just conservation of energy. What happens with the battery is that it provides energy to the current. All the energy needs to be used up by the time it gets back to the battery. So this voltage, 9 volts, is what's provided, and it'll push this current along. And the more voltage you have, the more current you're going to have. Well, we're kind of restricted on voltage right now. We need to find out what current is. So 250 is going to be over here. So I've got 9 over 250. What is that exactly? 9 over 250 gives me about 0.036. 0.036, and that's going to be in amps. If I move that over 1, 2, 3 times, I've got 36 milliamps. All right, and that's going to be our current for this thing. So what happens is that as this current starts to move, imagine this, these electrons are moving. I know it's a flow of positive charge, but as these electrons are moving, they're passing off energy. They're making these resistors get hot, and maybe even get so hot that they light up, and that would be a light bulb. But you can figure out how much energy they're getting by another equation, and that's going to be the power equation. So this is power. Power is equal to IV in a circuit. And if we plug in Ohm's law here, it's also equal to I squared R, or V squared over R. So there's like these 3 renditions of power. And power is measured in the watt. Okay, or sometimes in the kilowatt. And in this circuit here, we've got P equals IV, so I is going to be 0.036. The voltage being used in this whole thing is going to be 9, and if we multiply 9 by 0.036, I get 0.324 watts. So this little simple circuit right here is essentially putting out 0.324 joules per second that we run it. This resistor, however, if you wanted to figure that out, we'd say, all right, this resistor is using how much energy or how much power does it have? We're going to use let's use this one. I squared R, so 0.036 squared divided by R, which is 100. And then I got 0.036 squared over 100 gives me something really, really tiny. And I wonder if this is even right. Wait a minute. Why did I divide that? That's not right. I squared R, so 0.036 squared times R. There you go. 0.036, glad I caught that. Times 100. There you go, 0.1296 watts. So of our 0.324 watts, we're using 0.1296 watts right there. And then the other one should be the difference for the 150 ohm, which, looking at it, it's got a higher number to it, so that should be right. So there you go, I'm going to stop this right now. It's a 19-minute video. Bye-bye.